This is the lecture for Basic Probability, the start of Chapter 7. For probability, we're trying to figure out the odds that something will happen, or the percent of the time that an outcome will happen. Some of the vocabulary we use is that there will be an experiment. So, and don't get too caught up in the statistical vocabulary. We don't use it a whole lot in this course, but the experiment, for instance, could be to roll a die. So die is singular for dice. One of them is called a die. And then whatever we're going to target that we want to figure out the probability of, we're going to call capital E for our event. Our event will be to roll a 5. Then there's a sample space of all the possible outcomes for this event. That's capital S. In this case, the set would be you could roll a 1, a 2, a 3, a 4, a 5, or a 6. Okay, then to figure out the probability of rolling a 5, you find the total number of possible outcomes. So you count how many elements are in that set, and there are 6, and they call that N of S. Then the total number of elements in this sample space that would be considered a success is only 1. It's if you roll a 5. And again, the N of S and N of E, that's the number. You're counting how many successes. Then the probability of event E, so the probability of rolling a 5, it's the number of ways to have a success. There's one outcome that was considered a success out of the total number of possible outcomes, which was 6. So the probability would be 1/6. Probability is always a number in between 0 and 1. 0 would be an impossible event. There's no way it could happen. 1 would be a certain event. 100% of the time it's going to happen. All the probabilities land somewhere between 0 and 1. In WebAssign, if they're asking for a probability, it needs to be entered exactly. So that fraction of 1/6 is exact. You couldn't enter it as a decimal, because as a decimal, the 1/6 repeats forever. So don't enter it in that format. And generally, the problem will say to use a fraction, or it might say to enter it as a decimal, but to round to 3 or 4 decimal places. Okay, let's try this again. Our experiment will be to roll a die, but this time our event, or what we're targeting, what we're trying to count, will be to roll an even number. Our sample space is the same. Now the number of possible outcomes is still 6, but the number of successes, now there are 3 outcomes in the sample space that would be considered a success because they're even numbers. So the number of the event, the number of ways the event can happen, is 3. So the probability of rolling an even number would be 3 successes out of 6 total possible. WebAssign will take it as 3/6, but you can reduce it down to 1/2. That's fine. Now, as a decimal, that is a 0.5 and it doesn't repeat. It's a terminating decimal, so any of those would be accepted in WebAssign. This time our experiment will be to toss a fair coin. We're going to toss it twice. And the event that we're going to consider a success would be if both tosses turn out to be tails. So the sample space would be all the possible outcomes. So we could have heads on the first toss and heads on the second. That's one outcome. Heads on the first toss and then tails, tails and then heads, tails and tails. So there's all the possible ways that the 2 tosses could turn out. The number of possible outcomes, so I'm counting how many, 1, 2, 3, 4. How many of those would be considered a success? Well, the success was only the 2 tails, so it'd be 1. So the probability of tossing a coin tails twice is 1 success out of 4 outcomes, or 0.25. We'll keep the same experiment. Let's toss a fair coin twice. This time the event will be you get 1 heads and 1 tails, but it doesn't matter which order. Our sample space is still the same. The number of possible outcomes is still 4. The number of successes, though, be either one of those. So I have 2 successes out of 4 possibilities. So the probability is 1/2 or 0.5. Okay, now we've got data in a table, and the table gives percents of employees at the ACE company in each of 3 salary brackets, less than 60,000, between 60,000 and 100,000, and more than 100,000, and then categorized by the sex of the employee, male and female. An employee is selected at random. Okay, that's the experiment, is to select one employee and then find the probability that the person is female and less than 60,000. Okay, now this is different because I don't have a total number of possible outcomes. What I have is that all of these percentages should add up to 100% of the employees. So what's the probability that the selected person is female? So I know I'm on this bottom row at least, and makes less than 60,000. That would be right here. That's the only part of this data that meets the criteria, and that probability is already stated as a percent. So 36%, you could write it as 36 out of 100, turn it into a fraction. It would be more common in this case to write it as a decimal. Second part, what's the probability that the selected person makes at least 100,000, so 100,000 or more? That would be both of those. So combining those together would be 6%. You could write it as 6 out of 100 or 0.06. And finally, what's the probability that the person is male or makes less than 60,000? So that or says either any male would be fine, so all of those are considered successes, or anyone who makes less than 60,000. Well, I've already counted those, so I can also include these 36% of females. Then I can add that all up. 24% and 19% and 5% and 36% will make 84%. So that probability would turn out to be 0.84. Okay, now, if you notice, there's a slightly easier way to go about this, which is I've added up those 4 that are circled in blue. I could also take the rest, which is 16%, and take everybody except those. So take the 100% minus 16%, or 1 minus 0.16. That would also get me to the 0.84 number. Sometimes with probability it's easier to count up the part that we don't want and then complement it, take it away from 100% to get the rest. In a game where only one player can win, the probability that Jack will win is 1/7 and the probability that Bill will win is 1/5. Now between those two possibilities, that's not 100%, so there could be somebody else that could win the rest of the time. First, find the probability that one of Jack or Bill, either one of them, will win. So if Bill wins, I'll consider that a success, and if Jack wins, I'll consider that a success. So the way that you do this probability for either Jack or Bill is I take the probability that Jack will win and I just add it to the probability that Bill will win. And that gives me the combined probability. So I need to do 1/7 plus 1/5. Let me get a common denominator, so I'll multiply by 5. So 5 35ths, and over here I need to get a common denominator, multiply by 7. 7 35ths, add that together, 12 out of 35 times. So the probability that one or the other of them will win, they'll win 12 times out of 35. How would I find the probability that somebody else will win? Well, I don't even know, like they didn't tell me how much that is. But what I do know is that if it's not Jack and it's not Bill, then it's 100% take away that 12 35ths, or common denominator. 35 take away 12 is 23 35ths. So between those two options, we covered everything that could happen. Either Jack or Bill wins, or someone else wins. And between those two should be all 35 options, or 100% of the possible outcomes. Okay, let's talk for a minute about an OR event. So the probability that event E or event F happening. So if E happens, that'll be a success. Or if F happens, that'll be a success. Either one. This is defined to be the probability of E happening added to the probability that F happens. But then if it's possible for E and F to happen at the same time, you have to subtract that off. So for instance, let's look at this example. Out of 100 students, so that would be the number of possible outcomes, would be 100, 20 can speak French. So the number of French-speaking people is 20, and 12 can speak German. Number of German, but there's 4 that can speak both of them. So number of French and German is 4. If one student is picked at random, that's the experiment, is to pick a student, what's the probability that he or she can speak French or German? So either one of the languages, okay, you don't have to have both. So probability of F or G, probability that they speak French, plus probability that you pick a person that speaks German, take away the probability that you pick a person that spoke both. Probability of a French-speaking person, 20 successes out of 100 total students. Probability for German is 12 out of 100. Take away the probability that they speak both is 4. So 20 plus 12, 32 minus 4, that's 28 out of 100. You could enter it as a reduced fraction, or you could enter it as a decimal. To illustrate why we have to subtract off the probability that they do both, I'm going to draw a diagram picture. It's called a Venn diagram. And anything that's inside this first circle will be French speakers. Anything inside the second circle will be German speakers. Well, in this middle part are the students who can speak both French, because they're inside the first circle, and German, because they're inside the second circle. So there are 4 students that are here. Okay, now for total French speakers, there need to be 20 people inside this circle, but 4 of them are already accounted for. So there must be 16 of these 20 French-speaking students that only speak French. They don't speak German. Then look at the German-speaking circle. There have to be a total of 12 students here, so there would have to be 8 more of them besides the 4 that speak both languages. So there's the 20 French speakers, the 12 German speakers, and 4 that speak both. Now if you want to find the probability that a student speaks French or German, that would be these 16 French only, plus these 4 that speak both, plus those 8. That gives me 28 out of a total number of 100 students. Okay, now let me try to do this again and illustrate why we need to subtract off this extra part. Probability of French would be these 16 people in this region plus those 4 people here. There's the 20 French speakers. Plus probability German is these 4 people plus these other 8 people right here. Now if I just added those together, I would get 32. But see how it counts those 4 students, these, the bilingual students, it counts them twice. So we have to subtract off that extra part that got counted twice. And that's why it comes down to 28. Okay, now, and that's all out of 100. The Watch It guy is going to use this formula, and he'll use that syntax. If you're using my homework videos, I don't use the formulas as much, and look, I can't even write them right. Sometimes I use capital P and sometimes I use PR. Okay. I generally draw a picture and I just circle the parts that count as successes. Let's talk about how you figure out a sample space. Let's have the experiment be that we're going to toss a coin 3 times. So the sample space would be all the different ways that that coin could turn out. So we could have heads and heads and heads. Or we could have heads and heads and tails. Or we could have tails and then heads and maybe tails. Or we could have heads and then tails and tails. Or you can quickly see that it would be hard to figure out if you got all of the possibilities. So there's something called a probability tree, and I'm just going to show you how to draw one. We're going to use it a lot more in the next section. Each decision is going to have a branch on this probability tree. So starting out, our first event happens right here at this first node. So this is just the start. There's 2 ways that that can turn out. It could be a heads or it could be a tails. Okay, this is our first coin toss. Okay, then for each one of those, we're going to toss a second time. The second coin could be either heads or tails. And similarly here, either heads or tails. That's our second coin toss. Now we have to do our third coin toss. Could have 2 possibilities for the third toss: heads, tails. Heads, tails, heads, tails, heads, and tails. Okay, now we're just going to follow the branch, follow each branch of the tree and write down the sample space. So heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. I've done all of the possibilities where the first branch went up. So now first branch is going to go down, be tails. Then heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So the number of outcomes in the sample space: 1, 2, 3, 4, 5, 6, 7, 8. Now if we wanted the event to be get exactly 1 head, I don't care if it's on the first coin, the second coin, or the third coin, just exactly 1, then the number of successes for that event would be, there's 1, 2, 3. And the probability for exactly 1 head would be 3 out of 8. Okay, that's a brief introduction to probability. We've talked about an experiment, an event, a sample space, how to count a number of successes, how to figure out a probability, what to do with an OR, and how to use a probability tree to help you count the number of outcomes in a sample space. Between this brief introduction and the specific help on the homework videos, you should be able to complete your homework.